Sketch the graph of the function f of x equals 1 divided by x squared minus 1 by determining the parts a through I. F of x equals 1, a constant, divided by x squared minus 1, a polynomial. We can factor the polynomial. It is a difference of squares. It factors into x plus 1 and x minus 1. The domain requires that the denominator cannot equal to 0. So x plus 1 times x minus 1 cannot equal to 0. Since it's factored, we can see from the x plus 1 factor that x cannot equal negative 1, and from the x minus 1 factor, x cannot equal positive 1. So for part A, the domain will be all real numbers except negative 1 and positive 1. It will start from negative infinity and go up to negative 1, not including it, round bracket. Union, start up again at negative 1 and go up to positive 1, not including either, round brackets on both. Union, starting up again at positive 1 and going to positive infinity, not including the positive 1, round bracket. That domain is all real numbers except negative 1 or positive 1. For part B, we want to determine if there is any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x is made up of, in the denominator, an even power of x, which will have y-axis or even symmetry, subtracting a constant, which always has y-axis or even symmetry. Since they match, the overall expression will be even. The numerator is a constant, which always has y-axis or even symmetry. So we have an even over an even. Since they match, it will be an even. So f of x will have y-axis or even symmetry. F of negative x is 1 divided by negative x squared minus 1, which is 1 divided by, a negative squared is a positive, and then x squared, and then minus 1. Comparing this result to the original, it is exactly the same as the original. So f of negative x equals f of x, which is the condition needed to have y-axis, also known as even symmetry. This means that the graph will be its own mirror image over the y-axis. We will be sure that that is the case. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate back into the original function, so y equals f of 0, which is 1 divided by 0 squared minus 1. 1 over 0 squared is 0, and then minus 1 is negative 1. And 1 divided by a negative 1 is a negative 1. We have an x-coordinate of 0. We found a corresponding y-coordinate of negative 1. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y, which is f of x, will be set to be 0, and we set it equal to the numerator of f of x after any factors from the denominator have canceled with the numerator. Comparing the numerator to the denominator in the original function, there are no factors that will cancel. If there is, those will potentially be holes to the graph. We can now take y, which is f of x, set it equal to 0 and set it equal to the numerator of the function, which is a 1, and solve for all x's. There are no x's to solve for, so for x-intercepts, there will be none. For part E, we want to determine the vertical asymptotes. This is done by taking the denominator in its factored version and setting it equal to 0, and solving for all x's. After canceling with anything in the numerator, we have no factors in the numerator to cancel out, so both these factors remain, and we solve for x, and x equals negative 1, and x equals positive 1 will be the two vertical asymptotes. We can determine the behavior around each of the vertical asymptotes. Starting with the x equals negative 1 vertical asymptote, we can look on the left side by taking the limit as x approaches negative 1 from the left side, of the original function, it's best to write it in its factored version. 1 over x plus 1 times x minus 1. The numerator is a 1. The denominator, we can plug a negative 1 into the first factor. Negative 1 plus 1 is a 0. However, we're approaching negative 1 from the left side, which means we're more negative than negative 1. When added to a positive 1, it will be a negative number while approaching to 0. So it will be a negative 0. Plugging in a negative 1 to the second factor will give minus 1 minus another 1. That's a negative 2. The numerator is a positive 1. The denominator is a negative times a negative, which is a positive, and 0 times 2 is a 0. Positive over positive is positive. Non-zero over 0 is an infinity, and we have positive infinity. We can determine the behavior on the right side of the x equals negative 1 vertical asymptote by taking the limit as x approaches negative 1 from the right side of the function written in its factored version. The numerator is a 1. The denominator for the first factor, plugging in negative 1 will give a 0, but we're approaching negative 1 from the right side, which means we are less negative than negative 1. When added to 1, that will be a positive number, but it is approaching 0, so it'll be a positive 0. Plugging in a negative 1 to the second factor, minus 1 minus another 1 will be a negative 2. In the numerator, we have a positive 1. In the denominator, we have a positive times a negative, which is a negative, and 0 times 2 is a 0. A positive over a negative is a negative, and non-zero over 0 is an infinity. We can now look at the behavior around the other vertical asymptote, x equals positive 1. We can determine its behavior on the left side by taking the limit as x approaches positive 1 from the left side of the function written in its factored version. The numerator is a 1. In the denominator, plugging a 1 in for the first factor, 1 plus 1 is a 2. Plugging a 1 in for the second factor, 1 minus 1 is a 0. However, we're approaching 1 from the left side here, which means we're less positive than 1. Subtracting a 1 will be a negative number. It will approach to 0, but it will be a negative number, so it'll be a negative 0. The numerator is a positive 1. In the denominator, we have a positive times a negative, which is a negative, and a 2 times 0, which is a 0. Positive over negative is negative. Non-zero over 0 is an infinity. We can also determine the behavior on the right side of the x equals 1 vertical asymptote by taking the limit as x approaches 1 from the right side of the factored version of the function. The numerator is a 1. The denominator, plugging in a 1 for the first factor, 1 plus 1 is a 2. Plugging a 1 in to the second factor, 1 minus 1 is a 0. But we're approaching 1 from the right side, which means we're more positive than 1 here. Subtracting 1 will be a positive number. So while it's approaching 0, it will remain a positive number. And it will be a positive 0. The numerator is a positive 1. The denominator, positive times positive is positive. 2 times 0 is 0. A positive over a positive is positive. A non-zero over 0 is an infinity. And there are the behaviors around each side of each of the vertical asymptotes. For part F, we want to determine if there are any holes in the graph. This occurs when f of x has a numerator and a denominator, and once factored, there are factors that cancel completely out from the denominator with the numerator. The numerator and denominator did not have any common factors to cancel, so for holes, there will be none. For part G, we want to determine the end behavior, horizontal asymptotes or slant asymptotes. F of x has a numerator and denominator. The numerator is a constant, and the highest power term in the denominator is a power of 2. In the numerator, a constant is considered a power of 0. So the denominator has a higher power than the numerator, which means that it will have a horizontal asymptote of y equals 0. The horizontal asymptote is found by setting y equal to the limit as x approaches positive or negative infinity, as long as they are polynomials in the numerator and denominator. The limits will match to positive and negative infinity of the original function 1 over x squared minus 1. We do not need the factored version here. The numerator is a constant. The highest power term in the denominator is a power of 2. It's bigger than the numerator. So as x approaches positive or negative infinity, this will be equal to 0. And therefore y equals 0 will be the horizontal asymptote. For part H, we want to determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. All of this involves the first derivative, f prime of x. It will take a little bit of room to work out the first derivative, so this can be done on another page. F of x is 1 over x squared minus 1. Since the numerator has no x's, no need for a quotient rule here. What we can do is rewrite this by bringing the x squared minus 1 expression to the numerator. There's an implied 1 sitting there that we don't need to write. And it will be raised to the negative 1 power by moving it to the numerator. All we have now is a power rule with a chain rule. So the first derivative, f prime of x, will be bring down the negative 1, leave the inside alone, subtract 1 from the power, multiply by the derivative of the inside, which is the 2x. We can bring the constants together. The 2 can move out with the negative 1. Negative 1 times 2 is a negative 2. There is an x that can also move out front. And there is an x squared minus 1 to the negative 2 power. We can move that negative power to the denominator to become a positive power. We do want all powers in the derivatives to be positive. So moving it to the denominator, it becomes x squared minus 1 quantity to the positive 2. We want to fully factor the first derivative. The numerator does not factor since it's a single term, so we will leave it as minus 2x. But the denominator, being that it's a difference of squares, can factor. And since the quantity is squared, when we factor to an x plus 1 and an x minus 1 for the difference of squares, each of them have that matching power of squared coming from right here. There's the version of the first derivative we're going to want. So it was negative 2x divided by x plus 1 squared times x minus 1 squared. We have the first derivative written as a single fraction. All powers are positive, and it is fully factored. So we can set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, if we divide both sides by the negative 2, we get x equals 0. In the denominator, it's already factored. The x plus 1 factor will give x equals negative 1, and the x minus 1 factor will give x equals positive 1. We will now check to see which of these are in the domain. The domain's all real numbers except negative 1 and positive 1. So x equals 0 is in that domain, and it is a critical number. X equals negative 1 and x equals positive 1 are not in that domain. They are not critical numbers. We can now draw a domain line. It has no left end because it starts at negative infinity And it has no right end because it ends at positive infinity. However, it is not all real numbers. It's broken up at -1 and +1 by those being vertical asymptotes. So at -1, we have a vertical asymptote. It can be indicated by a dashed line. At +1, we also have another vertical asymptote indicated by a dashed line. So the domain is already broken up into 3 separate intervals. We can put all critical numbers on here in order. We have only one of them, and it's a 0, so it sits between the 2 vertical asymptotes. This splits the domain interval into 4 separate intervals. We can pick a test value in each of the intervals. The first interval is -infinity to -1. We can pick -10 in there. The next interval is -1 to 0. We can pick -1/2 in there. Next interval 0 to +1. We can pick +1/2 in there. And then +1 to infinity, we can pick a +10 in there. We can test the trend by plugging these test values back into the first derivative. We only care whether it is positive or negative, so the best place to plug in is the fully factored version, which is this one. A couple things about this. Each of the factors in the denominator are raised to an even power, which means they are going to be positive, and they will not affect whether the first derivative is positive or negative. In the numerator, the negative in front of the 2 will matter. We'll be sure to account for that. So the only portion needed to plug in is the full numerator, which is -2x. Starting with the test value of -10, -2 times -10 is a positive. We have a positive first derivative. This corresponds to an increasing trend. Plugging the test value of -1/2 into the portion of the first derivative that matters, -2 times -1/2, negative times negative, will be positive. We have a positive first derivative. This corresponds to an increasing trend. Plugging the test value of +1/2 into the portion of the first derivative that matters, -2 times a +1/2, negative times positive, is negative. We have a negative first derivative. This corresponds to a decreasing trend. And then plugging the test value of 10 into the portion of the first derivative that matters, -2 times +10, negative times positive is negative. We have a negative first derivative. This corresponds to a decreasing trend. We have only one critical number here, and right at the critical number of x equals 0, we have the trend change from increasing to decreasing. So x equals 0 will be a relative maximum. X equals 0 came from the numerator, so it's a normal relative maximum. We have an x-coordinate of 0, and we have a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 0, which is 1 divided by 0 squared minus 1. 0 squared is 0, minus 1 will be a -1, and a +1 over a -1 is a -1. So it has a corresponding y-coordinate of -1. We've seen this point already. It was the y-intercept up above. X equals -1 and x equals +1 were not critical numbers. They were vertical asymptotes. But we can see the trend behavior on each side of those and account for it as part of the graph. For part I, we want to determine the intervals of concavity and any inflection points. All of this will involve the second derivative, f double prime of x, which we'll take from the first derivative, but it's best not to take it from the fully factored version, and we'll need a little bit of room, so we can work this out on the other page. F double prime of x equals, in general, the more factored, the more difficult the derivative will be. So the best version to take the second derivative from will be this one here. It is a quotient of two expressions of x, so a quotient rule will be needed this time. derivative of the numerator, which is a negative 2, times the denominator left alone, x squared minus 1 squared, minus the numerator left alone, negative 2x, times the derivative of the denominator, which is a power rule. Bring the power down, leave the inside alone, subtract 1 from the power to be to the first power now, and then multiply by the derivative of the inside. And then all of this will be over the denominator, which is already squared, and then squared. In the numerator, we will leave the first term as is. The second term, we want to bring all the constants together. We have a negative implied 1, a negative 2, a positive 2, and a positive 2. Negative times negative 2 is positive 2, times another 2 is 4, times another 2 is an 8. So it'll come out to a positive 8. We have an x and another x, so x squared. And then we have an x squared minus 1 to the first power. And all of this is over x squared minus 1 squared and then squared again. We multiply the exponents, 2 times 2, which is 4. As a rule of thumb, in taking a derivative, the denominator will always increase its power only by 1. If we look, it's a power of 4. It was a power of 2. It's increased by 2. But that's because in the numerator, we have a common factor of x squared minus 1. We have a power of 2 here and a power of 1 here. We can factor out the lower power, which is the power of 1. And after factoring it, we'll be able to cancel in the denominator, and that will bring it down to a power of 1 higher than it was in the first derivative. It should become a power of 3. We want to fully factor the second derivative, and in the numerator there is a common factor of a 2 as well as the lower power of x squared minus 1, which we found out was to the first power. Factoring out the 2, this will become a negative 1, and this will become a positive 4. Factoring out the x squared minus 1 to the first power, factoring is division, division is subtraction of exponents. So we'll subtract a power of 1 from here, which makes it become a 1. So we'll have a negative times x squared minus 1. And this is already to the power of 1. Subtracting 1 from becomes a 0. Anything to the 0 is a 1. So I'll be left as a positive 4x squared. So we have a negative of x squared minus 1 plus 4x squared left after factoring. A negative of x squared minus 1 plus a 4x squared. Now that we factor out the x squared minus 1 factor, it can cancel with one of them in the denominator, leaving 3 of them in the denominator. In the numerator, we have a 2. Inside of the square brackets, we can distribute the negative in here, which will be a negative x squared plus 1. And then we have the plus 4x squared. And all this will be over x squared minus 1 cubed. We can combine like terms together inside the square brackets. The negative 1x squared and the positive 4x squared can combine to become 3x squared. We'll now turn it into parentheses. And we have a plus 1. And we have it over the denominator. We want to fully factor the second derivative. The numerator will not factor any further because we have a sum of squares. We have an x squared term and then it's added to a constant, and that does not further factor. The denominator, though, is a difference of squares. X squared minus 1 will factor to an x plus 1 and an x minus 1. Because it's cubed, each of these will receive that power of cubed. There's the version of the second derivative we're going to want. We found it to be 2 times 3x squared plus 1 divided by x plus 1 cubed and x minus 1 cubed. So we have the second derivative written as a single fraction. It's fully factored, all powers are positive. We can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, we can divide by 2, and we need 3x squared plus 1 to equal 0. Solving for x squared will equal negative 1 and then divided by 3. And then x will be plus or minus the square root of that negative 1/3. Because there's a negative inside of that even root square root, those x's will not be real numbers. From the denominator, it's already factored, so we can see that x will equal negative 1 and x will equal positive 1. We'll now check to see which of these are in the domain. The plus or minus square root of negative 1/3, those are not real numbers, so those will not be in the domain. The domain's all real numbers except negative 1 and positive 1, so neither of these will be in the domain either. So we have no x's that are making the numerator or denominator equal to 0 that are in the domain, so we have no candidate numbers. We can now draw a domain line. Line representing the domain. It begins at negative infinity and ends at positive infinity. But it does not include negative 1 or positive 1. Those were found to be vertical asymptotes, so they can be removed by indicating them as a vertical asymptote with a dashed line. So the domain is already split into 3 separate intervals. We can pick a test value in each of these intervals. There are no candidate numbers to further split any of these intervals. The first interval, negative infinity to negative 1, we have negative 10 in there. Negative 1 to positive 1, we have 0 in there. And positive 1 to positive infinity, we have positive 10 in there. We can test the concavity by plugging the test values into the second derivative. We only care whether it is positive or negative here. So we'll plug into the fully factored version, which is this version here. A couple things about this. In the numerator, we have a term of 3x squared in even power of x, and then it's added to 1, so that will always be a positive number. And then it's multiplied with a positive 2, so the entire numerator is positive and will not affect whether the second derivative is positive or negative. So the only portion that matters is the denominator. Since each of those are raised to an odd power, they can be positive or negative. Plugging in a negative 10 plus 1 is a negative cubed is a negative. Negative 10 minus 1 is a negative cubed is a negative. We have a negative times a negative, which is a positive. We have a positive second derivative, which corresponds to concave up. Plugging in the test value of 0 into the portion of the second derivative that matters, 0 plus 1 is positive, positive cubed is positive, 0 minus 1 is negative, negative cubed is negative, positive times negative is negative. We have a negative second derivative. This corresponds to concave down. Plugging in the test value of positive 10 to the portion of the second derivative that matters, 10 plus 1 is positive, positive cubed is positive. 10 minus 1 is positive, positive cubed is positive, positive times positive is positive. We have a positive second derivative. This corresponds to concave up. We have no candidate numbers here. X equals negative 1 and x equals positive 1 are vertical asymptotes. Since we have no candidate numbers, they're will be no inflection points. The concavity is still changing, but it's changing due to the vertical asymptotes here. We can now draw the graph. We have a vertical axis. We have a horizontal axis. We have a domain that is all real numbers except for -1 and +1. And we had found those to be vertical asymptotes, so we will graph those as vertical asymptotes on here. Usually indicated by dashed lines. We can label these. This will be the x equals -1 vertical asymptote. And over here, the same distance away from the y-axis, we'll have the x equals +1 vertical asymptote. We found there to be y-axis or even symmetry, which means that the graph should be a mirror image of itself over the y-axis. We'll be sure that that is the case. We found a y-intercept at 0, -1, so that'll be somewhere about right here. We can label this as 0, -1. We have no x-intercepts. We have the vertical asymptotes. They've already been graphed on here, but we can look closer at the behavior, starting with the x equals -1 vertical asymptote. According to the behavior here, on the left side of it, it's going to positive infinity. On the right side of it, it is going to negative infinity. That means that on the left side, the graph should be up here and approaching it. And on the right side, it should be down here because of the negative infinity and approaching it. We also have the behavior around the x equals +1 vertical asymptote. On the left side, we have it approaching negative infinity, and the right side approaching positive infinity. So on the left side approaching negative infinity, which means on the left side of it, it should be down here, and the right side approaching positive infinity, on the right side it should be up here. We found no holes in the graph. We have a horizontal asymptote of y equals 0. That's the x-axis, so we can put a dashed line here. And this horizontal asymptote is its end behavior. It should be approaching the y equals 0 or the x-axis on the left and the right ends of the graph. So we'll be sure that that is the case. Right at the point 0, -1, we found a relative maximum. So we will give this a relative maximum type of shape. It turns out to be the y-intercept that we had found earlier. And we found no inflection points, so the concavity will not change at any point, though from what we see here, it is changing around the vertical asymptotes. To the left of the vertical asymptote of x equals -1, we have a behavior of increasing while being concave up, and it should be approaching the y equals 0 horizontal asymptote, so it's going to be starting from here and curving up like so. In between the vertical asymptotes of -1 and +1, we have a trend of increasing to left of 0 while being concave down, and decreasing to the right of 0 while still being concave down. And we have the relative maximum there at 0, -1. So it's supposed to remain concave down the entire time, so it's curving downward. It's increasing on this portion while being concave down, and it's decreasing on this portion while being concave down. It's approaching -infinity towards each of those vertical asymptotes. To the right of the x equals +1 vertical asymptote, we have a trend of decreasing while remaining concave up. And it should be approaching the horizontal asymptote of y equals 0. So it should be approaching to here. And we can give it that type of behavior and that type of graph, which will look something like this. So we have the domain is all real numbers except -1 and +1. They are vertical asymptotes. And this is displaying the y-axis or even symmetry because the graph is its own mirror image over the y-axis. If we take this portion and flip it over the y-axis, or think of it as a mirror image, it overlaps itself to the left side of the y-axis. So it is showing that symmetry as it should. And we followed all the behaviors of the vertical asymptotes. Everything is checking out here. This will be the graph of f of x.